All right, so this is the part 3 of the right ventricular focused critical care echo series, and now we're going to go beyond the TR jet and look at a little bit more stuff that can give us information about right ventricular and pulmonary hemodynamics. So far in this series, we've really only looked at the TR jet and used the modified Bernoulli equation and principle to estimate PA pressures, or more correctly, right ventricular systolic pressures. Now we're going to move to some other views and try to get a sense of some of these hemodynamics. Now, I've shown this before. This is my hierarchical approach to assessing the RV. I think the apical four chamber is best. Then I like the inflow view. Now we're going to talk about the outflow view. Even though it's not as high in my hierarchy, the reason that's the case is that it's often difficult to get these images, but if you can get some beautiful information about hemodynamics. So let's skip ahead or skip down in the hierarchy and talk about the RV outflow view. So again, this is something that you're obtaining from really starting with a parasternal short axis view and sliding up a rib space or two. And what you'll end up getting, this patient has a beautiful example. I actually can see the inflow and the outflow here. But what you end up doing is you end up slicing the aortic valve in a transverse plane, and you end up getting the right atrium dumping into the right ventricle. So this is a bit of the inferior and the free wall, and then this is more the anterior wall of the RV that you're getting. And then you're able to actually see your PA going out this way with your pulmonic valve coming in and out of view here. So this is awesome because you can now get a lot of information about hemodynamics. In fact, if you were to get this kind of view, you could look at your RV inflow and look at your TR jet signal, and then you could look at a lot of the hemodynamics through the RV outflow tract, which is what we're going to talk about now. So when you're looking at the RV outflow tract, you're really looking at the area right at the level of the pulmonic valve. So first things I can glean here, I can look at my RV OT systolic Doppler signal, and I can measure a couple parameters that help me understand what the cardiac output is through the lungs, or the QP, as well as pulmonary vascular resistance. I can also pick up my pulmonary insufficiency jet in a lot of people, and that will help me understand what my pulmonary artery diastolic pressure is. So the focus here is all going to be around this pulmonary valve and its insufficiency jet. So first, let's talk about the acceleration time. So when I want to measure an acceleration time, I'm going to line up my pulse wave Doppler. I'm going to put my sample box just below the level of the pulmonic valve. This is a little bit too deep on this schematic, but just below the level of the pulmonic valve. And I'm going to be picking up a pulse wave Doppler signal that looks something like this. Now in this view, I've got some color Doppler going on as well, so you can see where there's flow as well as a pulmonary insufficiency jet. But I'm going to drop my pulse wave Doppler. It kind of keeps coming in and out of view here, but I'm going to drop it just below the valve so I can pick up this signal. So what exactly is the acceleration time? Well, the acceleration time is a surrogate for RV contractility as well as pulmonary vascular compliance. So this is a normal acceleration time. You can see there's this big pulsatile flow through the pulmonary artery which distends with each beat. That's a normal response. I can show that again. So RV contractility is normal, pulmonary artery distends substantially, and the acceleration time is actually prolonged. It's longer because there's a lot of capacitance in this blood vessel to accommodate that blood, and RV contractility is good. Now contrast that in the situation where RV contractility is diminished and or the pulmonary artery capacity is maximally distended. So in that situation, I have much less pulsatility, and my time to my peak velocity is actually much shorter because my contractility is down and I have a high pulmonary vascular resistance, high impedance, low capacitance state. So the pulmonary artery acceleration time actually reflects a few different things. It's really a reflection of the coupling between the right ventricle and the pulmonary artery. It measures my RV contractility. If I have better contractility, the time to which I hit my maximal velocity or my acceleration time is longer. If my pulmonary vascular impedance is high, that will start to shorten. So that's like running into a brick wall, right? If I'm running into a brick wall, I'm going to hit my maximal velocity much sooner than if I'm running into a soft surface, like jumping into a pile of pillows. And then it's also going to tell me about my pulmonary artery capacitance, and it's going to be inversely related. So when I have a lot of capacitance in the vessel, this systolic flow curve is going to take longer to hit its peak than when there's not a lot of capacitance. In other words, when the vessels are completely full with blood or have high pressures, then I'm going to hit my peak pressure earlier. Again, this is like running into a brick wall. This is like jumping into a pile of pillows. So when my PA acceleration time is 125 milliseconds or somewhere in that ballpark, I know I have good RV contractility and normal pulmonary artery capacitance. But in high pulmonary vascular resistance states, when my impedance is high, when my pulmonary artery capacitance is low, my pulmonary artery acceleration time starts to fall off substantially. So I just wanted to review some of the physiology here again briefly. I've drawn crudely drawn the pressure volume loops of both the left ventricle and the right ventricle. And if you've looked at these things before, you know about these Sagawa diagrams. This is your start of systole. And when you look at the end systolic pressure volume relationship, the slope of that line is the LV elastance, which is a marker of contractility. In fact, it is the marker of contractility. And for any given patient, assuming contractility is constant, when you subject this LV to different loading conditions, all of the curves are going to line up in a way that the end systolic pressure volume relationship will line up on this line. Now the RV looks a little bit different. The RV peak pressure is a little bit earlier in systole, but you end up having this sort of curve where the contractility is manifested in this line, the RV elastance line, and again, that's my end systolic pressure volume relationship. So as I said before, the pulmonary artery acceleration time reflects RV contractility in some ways, and we're going to show that in a moment using these types of diagrams. So let's assume this is a normal heart, a normal RV that has now been subjected to increased load. So there's acute volume overload of the RV. Well, this line is my elastance of my pulmonary artery, and as that gets steeper, i.e. pulmonary artery vascular impedance is higher or resistance is higher, then the intersection of these two things becomes higher. But my RV contractility still is the same. Now, as I really change loading conditions and I really overload the RV, actually RV contractility is going to fall off, and the slope of this is going to be much higher. Again, this is my RV elastance line, which reflects contractility, and this is my pulmonary artery elastance slope, which is going to reflect my pulmonary vascular resistance or impedance. So in this type of condition, you can actually start to understand why the acceleration time is much shorter. So here again, my green curve, I had a long acceleration time because my contractility was better and my pulmonary vascular resistance was lower. Here my acceleration time is smaller because I have a smaller stroke volume, lower contractility, and a higher pulmonary artery vascular resistance or vascular impedance. Again, the physiology is a little complicated. Simplest way to think about it, running into a brick wall, you can hit your acceleration time much sooner. Running into a wall of pillows, it is going to be a smoother landing, and your acceleration time will actually be much later in systole. So let's look at some examples. Again, somewhat of a counterintuitive measure, but in this example, I have a pulmonary vascular or pulmonary valve acceleration time or RVOT acceleration time of 125 milliseconds. So when I'm doing that, I'm taking my pulse wave signal, I'm measuring it from the point where there's no flow to the point of maximal flow. And as you can see, it's going to be about the same in all these examples here. That's the acceleration time, 125 milliseconds. In this case, it's normal. So again, it's a measure of RV contractility, reflects PVR. Here are some notes on it, though, that are worth considering. The utility of this measure is going to decrease when my patients are tachycardic, and that's simply because my systolic time is going to be shorter. So my acceleration time will naturally be a shorter duration because now the time I'm spending in systole will be shorter. Again, acceleration time is thought to reflect pulmonary vascular resistance, but it does not directly measure it. It actually is measuring many things that go into pulmonary vascular resistance. And the acceleration time, though, is a good way to estimate mean PA pressures nonetheless. So when I can't get a good TR signal, which they say is about a quarter to a third of patients, you can't pick up a TR signal, I can use my acceleration time as a pretty rough surrogate, but a pretty good surrogate of my mean PA pressures. And they're related by this equation here. So my mean PA pressure can be estimated from 79 minus 0.45 times my acceleration time. And again, you can see from this equation here that higher acceleration times are going to result in lower mean PA pressures, whereas lower acceleration times, because it's negative, will give me a higher mean PA pressure. All right, that's it on acceleration times. A little bit of a counterintuitive measure, a little bit complicated physiology, but can be very helpful for understanding pulmonary artery pressures and pulmonary vascular impedance. Now we're going to move on to talking about the QP, measuring the QP, or the cardiac output through the pulmonary circuit. Now you might ask, when is that helpful? Well, we'll talk about that more in a moment, but first let's just talk about how to measure it. This is done the same way as you would do if you're trying to measure cardiac output, systemic cardiac output, using the LVOT diameter, but here we're going to look at the RVOT diameter. So to measure my pulmonary circulation cardiac output, I need to know my right ventricular outflow tract diameter, and I need to measure my right ventricular outflow tract diameter velocity time integral just before the valve is opening. That means I'm going to put my pulse wave Doppler box here. Now in this example, I measured my RVOT diameter at 2.9 centimeters. That's a pretty big PA. This patient had a little bit more normal of a right ventricular outflow tract diameter, which is 2.1 centimeters. And now, in this patient, I'm going to measure my velocity time integral. Now remember, my velocity time integral is putting my pulse wave Doppler just below the pulmonary valve, and I'm going to measure the area under this curve. This is my systolic ejection curve on my pulse wave Doppler, and the area under this curve is called my velocity time integral. And the principle of the velocity time integral is this. If I know the diameter of the circle that this velocity time integral is going through, and I know the area under that curve, I can actually figure out how much blood volume is going through in that time, which is another way of saying I can figure out my stroke volume. So stroke volume is pretty simple. If I know the area of the circle and I know the velocity time integral going through that circle, I can get a stroke volume. So that's pi times my radius, my RVOT squared, times my velocity time integral. It's the same thing you'd see if you were measuring systemic cardiac output through the LVOT. In this example here, I found that my QP, if I plug in this equation here, is going to be 3.6 liters per minute. Now, if you want, you can pause here and do the math yourself. All I'm doing is taking a diameter of 2.1. I got to cut it in half to get a radius, so that's 1.05. 1.05 squared times pi times my LVOT VTI, which in this example, 14.7 centimeters, 14.7. And then this 72 is the heart rate of the patient at the time I did this study. So from that, I can get my pulmonary vascular circuit cardiac output. And you might say, well, why would I measure that? Why don't I just measure my systemic cardiac output? Well, the times to do this would be if you had a significant shunt or an intracardiac lesion or something. And that was actually relevant in this patient. This patient had some shunting. We could see that was the case. And we wanted to see if some of that was really an intrapulmonary shunt and how much pulmonary vascular flow there was relative to the cardiac output. In the end, they ended up being about the same, so I wasn't sure what to make of it. I'm not a congenital cardiologist. I'm not sure if I could understand QP, QS otherwise, but it's something worth potentially doing in some patients that may have shunt, particularly if they had some, if there was some concern that there was increased circulation through the pulmonary circuit relative to the systemic circuit or vice versa. Okay, so if I want to do some other cool stuff here, I can do this. I can estimate my PVR for my velocity time integral. Now this is actually pretty cool. So we talked about we can estimate PVR or understand PVR if we look at the acceleration time. But I actually can estimate my PVR for my velocity time integral too. And here's how I do that. I'm going to start with Ohm's law. With Ohm's law, I know that voltage is my current times my resistance. And we have the equivalent equation when we use hemodynamics. We can look at my pressure gradient being equal to my flow times my resistance. Now, if we were to rearrange that equation, we could say that resistance, in this example in the pulmonary circuit, my pulmonary vascular resistance is equal to my pressure gradient divided by the flow, or the cardiac output. Now, if we had a swan, we would do it this way. We'd say my PVR is 80 times my mean PA pressure minus my wedge pressure divided by my cardiac output, which I would measure for my thermal dilution on my swan. However, I can actually capitalize on a different pressure gradient and a different flow to get an estimate of PVR. Now, this is kind of clever. I'm actually going to look at my pressure gradient by looking at my TR velocity, my maximal TR velocity. Now, that's not what I'm looking at when I'm looking at a swan, but we'll get back to that in a minute. But I can get some pressure gradient that reflects my RV systolic pressure, And I can get a flow. That flow is going to be characterized by my velocity time integral through my RVOT. That's a surrogate of flow, right? I'm going to ultimately use that for a stroke volume and a cardiac output. And using these two surrogate measures, I can actually estimate PVR. So it's pretty cool, right? Now, it's not actually measuring pulmonary vascular resistance directly, right? I'm actually looking at a TR jet signal to get my pressure gradient. It's not the pressure gradient at all that we'd use on a swan. That is the mean PA pressure minus the wedge. However, some clever person figured out that I can estimate PVR by multiplying 10 times my velocity of my TR jet, my maximal TR jet velocity, divided by my velocity time integrals for the RVOT. So again, I'm using a pressure gradient, I'm using a flow surrogate, not the ones we typically use with a swan, but I can still estimate my PVR from that, which is really pretty cool. Now this has actually made me wonder, can I estimate my PVR from other parameters? Now, if you've looked at my diastology stuff, you know that you can actually get a surrogate of your wedge, or you can actually almost directly measure your left atrial pressure from your diastology. You also might recognize that you could estimate your mean PA pressure if you knew the mean TR jet velocity. So in the last picture, we were looking at the maximal TR jet velocity. But if I was to look at the entire curve here, and let the machine calculate the mean TR jet velocity from this entire curve, I could actually get a surrogate of my mean PA pressure. In fact, that reflects my mean PA pressure. It reflects my mean RV systolic pressure. Do you follow me? So looking at my mean TR jet velocity signal, it's a surrogate of my mean RV systolic pressure, which is another way of saying my mean PA pressure. I can also get my cardiac output by actually measuring it using the RVOT VTI, and not just using the VTI alone, but looking at the radius of the RVOT, multiplying it by pi times my heart rate. And then I actually can get my wedge pressure or my left atrial pressure from my E to E prime ratio, right? We talked about this before in the diastology series. Left atrial pressure equals roughly lateral E velocity divided by lateral E prime velocity plus 4. So I actually can plug all three of those things into this equation and also estimate my PVR. Now this is not nearly as valid, but if you assume that the mean PA pressure from your mean TR jet velocity is accurate, if you assume that the left atrial pressure is somewhat accurate from this equation, and you have a good cardiac output, you actually can measure PVR somewhat directly from your new swan, which is your echo probe. All right. So we've talked a lot about acceleration time. We've talked about velocity time integrals. We've looked at some other hemodynamics I can get from the acceleration time and the velocity time integral. The last thing now we're going to talk about is my pulmonary insufficiency jet. Now usually this is a low flow enough velocity that I can use pulse wave Doppler, but for regurgitated signals you should probably be using continuous wave Doppler just to be sure you're picking up the maximal velocity. And my jet here is going to be used to estimate my PA diastolic pressure. And again, we're going to capitalize on Bernoulli's principle here, in the Bernoulli equation. My gradient is equal to 4v squared. In this case, the gradient is the gradient between my PA diastolic pressure, which is when the insufficiency jet is flowing, and my RV and diastolic pressure. That's the gradient of interest. And here I'm going to use my pulmonary insufficiency jet at the end of diastole, square it, multiply by 4, and I'll get a sense of what my RV and diastolic pressure is because I'll know what my PA and diastolic pressure is. Sorry, I'll know what my PA diastolic pressure is because I'll have some estimate of my RV and diastolic pressure. So let's work through the math. Let's work through an example. Here, again, I used pulse wave Doppler. It was okay because the signal wasn't very fast. And I got an end diastolic pulmonary insufficiency jet velocity of 9.09 centimeters per second or 0.91 meters per second. If I plug that in, square it, multiply by 4, that is actually equal to 3.3. It's a small gradient. In fact, I have that gradient right here listed for me. The machine did the Bernoulli for me, 3.3. Very small gradient. And if I assume my right ventricular end diastolic pressure is equal to my right atrial pressure, which again I can measure from a CVP, I can look at my IVC and try to get a ballpark of it, then I know my pulmonary artery diastolic pressure is just that right atrial pressure plus this pressure gradient, which we just measured up here. Does that make sense? So again, Bernoulli's is always telling us about gradients, not absolutes, gradients between two chambers. So the pulmonary insufficiency jet is a gradient between PA diastolic pressure, RV end diastolic pressure. If I can substitute right atrial pressure for my right ventricular end diastolic pressure, I can measure PA diastolic pressure by getting this PI jet. In this example, it works out to 9 millimeters of mercury, which is quite low. And I'd expect this to be pretty close to my wedge pressure if I used the Swan. I'd also expect this to be pretty close to my left atrial pressure estimates for my diastolic stuff on the left side. So this is a pretty cool way to estimate PA diastolic pressure. All right, so let's take an example here. What is this patient's pulmonary vascular resistance? Likely very high, probably a little high, not very high, or there's inadequate data. Good. This is flashing back to earlier in this talk, but we said that pulmonary artery acceleration times under 75 milliseconds were abnormal. It's been measured multiple times here. Each time it was about 60 to 65 milliseconds. So in this case, the PVR is probably quite high. And this is the table again. Normal, usually in the range of 125 milliseconds, plus or minus 25 milliseconds. High PVR states, usually less than 100, often less than 75. If you have it less than 60, then you're really dealing with significant elevation of pulmonary vascular resistance and impedance. The other thing you'll pick up from this signal, which I haven't talked about, but is a nice little thing to mention here, is this patient has double notching, or what might be called a W sign, in their pulse wave Doppler signal through their pulmonary valve in the right ventricular outflow tract. And that is another sign of pulmonary hypertension. You get the second hump in your systolic pulse wave Doppler signal. All right, let's take another patient. This patient's CVP is measured at 12 millimeters of mercury. I wish I knew what their PA pressures were, but I can't pick up a pulmonary insufficiency jet. However, I do get a decent TR velocity jet. And when I play with the machine, I got a TR max velocity of 3 meters per second. And then when I ask the machine to give me the mean gradient over the entire systole, it tells me the mean gradient is 22 millimeters of mercury. So what are my PA pressures? Well, if I had a PI jet, what could I measure? I could try to measure my PA diastolic pressure, but I'm not going to be able to pick that up here. So am I going to be able to figure out what that is? Perhaps with this data alone, it's good enough. So if you want, you can pause here and do the math or try to work through it before looking at my answers. But let's start with the PA systolic pressure. We know that's going to be right atrial pressure plus my TR velocity at its maximal velocity squared times 4, which in this case equals 48. So remember, this is a gradient between right ventricle and right atrium. If I know my right atrial pressure, then I can figure out what my right ventricular pressure is because it's accounted for in that gradient, and that's 48. PA systolic pressure, assuming there's no pulmonary valve stenosis, is going to be the same as my right ventricular systolic pressure, which is going to be 48 millimeters of mercury here. So the patient has some degree of pulmonary hypertension. I can also figure out what my mean PA pressure is from these curves because I have a mean gradient. So if I take my right atrial pressure and add my mean gradient, I'll get my mean PA pressure. And from that, again, it'd be nice to be able to measure the PA diastolic pressure somewhat directly by having a pulmonary insufficiency jet. But if I don't, I can go back to this equation and say my mean PA pressure is typically about 1/3 of my PA systolic pressure and 2/3 of my diastolic pressure. So if I were to rearrange this equation, I actually will find that my PA diastolic pressure in this patient is 27 millimeters of mercury, which is actually quite high. So I can use some cool math here, and even if I can't get my pulmonary insufficiency jet, I can just use my TR velocity jet to start making some inferences about my PA diastolic pressure. Now, this isn't validated. This has not been something that's been measured with swans. But again, in the ICU, we're trying to get some rough estimate of what's going on with the patient and hopefully not having to float a swan to get some information about pulmonary hemodynamics. And as we can see from this lecture, using TR jet velocity, looking at pulmonary artery acceleration time or RVOT acceleration time, and looking at pulmonary insufficiency jets, we can actually make exceptional inferences about pulmonary artery pressures and right ventricular systolic function.